Good afternoon. So today we're going to learn a method of a way to deal with a definite integral when the classical means of integrating won't work. So last lesson we actually went over the last topic on techniques of integration for this class. And it's important to remember that there are plenty examples in real life in which the actual integral that you try to compute cannot be integrated by classical means. It cannot be expressed by classical functions, in other words. And some of the functions for which this happens are surprisingly easy or with innocent look, so to speak. One example I wrote here already. So for example, if you want to compute the antiderivative of e to the minus x squared, you would be surprised that actually it's not going to work with any known integration technique, although the integral does exist. So in that case, we rely to approximating the integral. It's important to point out that we know already how to do this. Remember that in Calculus 1, we introduced the concept of a definite integral by approximating that integral with a Riemann sum. And the Riemann sum, remember, is nothing but a sum of areas of rectangles that approximate the area between the graph of the function, the graph of f of x, and the x-axis. So basically we do kind of the same thing, except that we don't restrict ourselves just to rectangles. And the first method that I'm going to show you actually involves rectangles, but with a specific way of choosing the intermediate point. Because remember, those rectangles come from partitioning the domain of the function into equally spaced subintervals. So x1, x0, x1, x2, somewhere in the middle. Here, let's say it's xi minus 1, xi, and then all the way up to xn. The rectangles are constructed by raising a perpendicular over the x-axis on each subinterval by choosing an intermediate point where you raise that perpendicular. So the midpoint rule, as the name implies, means that you choose the midpoint of that subinterval to raise the perpendicular. Depending on how the function looks like, some of the methods will give you smaller errors than others. So for the purpose of today's lesson, I'm going to basically go over two methods, the so-called midpoint rule and the trapezoid rule, just to see how each of them gives you a different error of approximation. There are more than two methods, but I'm going to just go over these two only. So the midpoint rule, so let's start with the midpoint rule. And for simplicity, imagine that the function looks like this. I always choose the function to look like, to choose the function that is above the x-axis. It doesn't have to be above the x-axis, but it's easier to visualize it this way. And then, like I said, you have that partition, x0, xn, and somewhere in the middle you have that subinterval. I, by the way, when I say xi minus 1 xi, I mean that I is between 1, 2, all the way up to n. So that's a typical subinterval indicated here on the domain. And we're going to choose the midpoint where we raise the perpendicular to construct the rectangle. So we're going to denote the midpoint by xi bar, just to make an association with the index of the endpoints here of the subinterval. And a quick formula to find the midpoint of any segment is the semi-sum of the endpoints over 2. The semi-sum of the endpoints. That's how you find the midpoint. So here, if this is in the middle, this is xi bar, we're going to raise a perpendicular over it, construct a rectangle, and the area of that rectangle will be part of the summation, which approximates the Riemann integral. And because we choose this partition to be equally spaced, the distance between any two intermediate points is the same, we're going to denote that distance by a delta x, as is commonly done or when we do these notations. So that being said, then the integral from a to b of f of x dx will be approximated by the sum of the areas of these rectangles. So delta x times f of x1 bar, so that'll be the first segment here from x0 to x1. Then delta x times f of x2 all the way up to delta x times f of xn bar. So let's write it one more time here. So the integral from a to b of f of x dx is approximated, because we can pull out delta x, by delta x quantity f of x1 bar plus f of x2 bar all the way to f of xn bar. So this is the formula for the so-called midpoint rule. This is another case in which the formula and the way to present it sometimes looks worse than in practice. So once you move to examples, I hope it's going to be much clearer. And let's actually do this with the example that I mentioned here on the top of the page. And let's say we want for that example, right, to compute the integral, to approximate the integral of e to the minus x squared on the interval 0, 4. Let's say we want to use n equals 4. Typically I use n equals 4 in homeworks or exams to make it, in exams or quizzes, to make it shorter. If you want to use more points, usually you do this with computer algebra systems, because that's not practical to do by hand, obviously. And even for this, you need a calculator to actually do the computation to confirm with me. So let's say n equals 4. That means the domain 0, 4 is going to be split into 4 equal pieces. So the first thing to do is to compute delta x, which is the length of the interval, the whole interval, which is 4, divided by 4. So that's 1. And that tells you how you come up with the endpoints on the partition. So here x0 will be 0, x1 will be 1, x2 will be 2, x3 will be 3, and x4 will be 4. The midpoints will be the semi-sum of each endpoint, of the 3 endpoints of each subinterval. So the first midpoint here will be 0 plus 1 over 2, which is 1/2. This is going to be 1 plus 2 over 2, that's 3 over 2. 2 plus 3 over 2, which is 5 over 2. 3 plus 4 over 2, which is 7 over 2. So in the notation in my problem, this will be x0 bar, x1 bar, x2 bar, x1, x2, x3, x4 bar. Because I starts from 1. So then you're going to write down the integral, the approximation of this integral by simply plugging in these quantities in the midpoint formula. So delta x is going to be 1 in my case, and then plug in 1/2 into the function, so that's e to the minus 1/2 quantity squared plus e to the minus 3/2 quantity squared, e to the minus 5 over 2 squared, and then e to the minus 7 over 2 quantity squared. So take a moment and do this with your calculator and confirm that this is approximately equal to 0.88613. All right, so on the next page, we're going to go over the so-called trapezoid rule, which right off the bat, I'm going to anticipate it's just the same thing, the same idea, but the only difference is that the overlapping figures, which will approximate the integral, are made of trapezoids. So the point of the lesson actually is to make you understand that this whole thing with this approximation doesn't have to involve rectangles. And depending on, like I said, depending on how the graph of the function looks like, other shapes could be more suitable. The important thing is, of course, to use shapes for which the area can be computed, because that's the whole point, right? I mean, if you cannot compute the actual integral directly, then you will use Riemann sums involving these types of shapes that you can find with their area. So stay tuned for the trapezoid rule on the next page. So in the trapezoid rule, let's take a moment, so pause the video to actually sketch this first and make sure you write down the notation of the partition the way I wrote it here. So far, just like before, we have a partition with n intervals. A typical segment or subinterval on the partition is xi minus 1 xi with I from 1 to all the way up to n. Again, the distance between each of these points is the same, and let's call that distance delta x. So the idea is that often maybe a better error of approximation can be achieved if, instead of picking intermediate points and raising perpendiculars to come up with rectangles like before, we can actually overlap and approximate the area between the graph and the x-axis by constructing trapezoids involving these points. Each trapezoid basically will have two bases given by the perpendiculars already raised at the points x0, x1, x2, and so on. So in other words, the first overlapping, the first piece that approximates the area would be this trapezoid. So you simply connect these 2 points where the perpendiculars over x0 and x1 meet the graph of the function, and we're going to compute the area of the trapezoid. So you see this piece here between this side on the top and the graph will be an error of approximation. So the way I drew this graph of the function, the first trapezoid will underestimate the actual area between the graph. Same for the second one. That's going to be the second trapezoid. This one is not clear if it's an underestimation or overestimation. Then a typical point or a typical trapezoid in the middle between xi minus 1 and xi, if you look carefully, this will be an overestimation of the area between the graph and the x-axis, and so on and so forth, right? So the last one will be this one here. So all I have to do now is to come up with formulas for the areas of the trapezoid and add them up together. So in case you forgot, the area of a trapezoid is equal to the semi-sum of its bases times the height. These trapezoids are actually tilted, right? I mean, the height is going to be, well, let me actually draw it here. So if you have a trapezoid in this shape, let's call this the smaller base, this is the bigger base, and this is the height, then the area would be the semi-sum of the bases times the height. So in my case, the height will be delta x. So this will be the height of each of these trapezoids. All right, so let's come up then with the formula. The area of the first trapezoid is going to be the first base, f of x naught plus f of x1. So the heights will be the y coordinates at these points, x naught, x1, and so on. So f of x1 plus f of x naught here divided by 2 times the height. That's the first trapezoid, and then we add the second. F of x1 plus f of x2 divided by 2 times delta x. The generic one in the middle will be f of xi minus 1 f of xi over 2 times delta x, all the way up to the last one, f of xn minus 1 plus f of xn over 2 times delta x again. So we need to write this in the more compact form. And notice that, and actually let's write again. So this will be the approximation of the integral, right? So the integral from a to b of f of x dx. So notice that we can pull out delta x over 2. And now pay attention that with the exception of the first term and the last one, all of them appear twice. F of x1 is added twice from the first and the second. F of x2 will be added twice. It's not written here, but the third one will be f of x2 plus f of x3 over 2. All the way up until f of xn minus 1, which will be paired with the one before it. So if you see the pattern here, all of them appear twice except the first and the last. So therefore the formula for the trapezoid, the summation here is going to be f of x naught plus twice f of x1 to f of x2 all the way up to 2f of xn minus 1, the one before the last one, and f of xn, the very last one. So basically, depending on the number of partitions, like for example, if you have a partition of involving involving only 2 segments, then you have only 2f of x1, just only one of them that appears twice. So only the ones are in the interior, except the first and the last one. So let's do the same example like before, the integral from 0 to 4 of e to the minus x squared using the trapezoidal rule. So we're going to apply this to e to the integral of from 0 to 4 e to the minus x squared dx. So the partition is really like before, right? And we don't need any intermediate points. We just plug in these numbers, right? So n equals 4. So if we use the same partition, then x naught is going to be 1, 0. And then x1 is going to be 1, x2 will be 2, x3 will be 3. So the integral from 0 to 4 e to the minus x squared dx is approximately equal to, remember delta x is 1 in this case, so it's going to be 1 over 2 f of x naught, that's e to the minus 0 squared, which is just e to the 0, right? So plus 2 e to the minus 1 squared plus 2 e to the minus 2 squared plus 2 e to the minus 3 squared, and the last one is just by itself e to the minus 4 squared. Once again, take a moment to use the calculator and check that the answer here will be approximately 0.88632. Now, if you use, for example, a computer algebra system like Maple or Wolfram Alpha, you will see that the integral from 0 to 4 of e to the minus x squared dx is equal to, let's see, that I wrote it somewhere. Yeah, it's equal to 0.886227. Now, the computer algebra system will still approximate this, but with a far more sophisticated method, with more, far more points in the partition. So I put this, you could think of this as basically the best approximation, right, given by the computer. And just to compare it with the answer given by the midpoint and the trapezoidal rule. So the midpoint will be an underestimation. Our answer in the midpoint rule using 4 segments was 0.88613, and then with the trapezoidal rule was an overestimation, 88632. Now, of course, the more points you pick, the closer you are to the exact value. So if you choose, for example, in either of the methods, it doesn't matter if it's trapezoid or midpoint rule, if I choose, for example, 100 points or so, you should be pretty close to the answer given by the computer. So the homework for this is very short, about 3 problems. I think Simpson rule is also asked in some of these problems, so ignore that part and just do only the trapezoid and the midpoint rule. And with that, that's it for today.